In this video, we will build vision transformer model from scratch using Pytorch package. So first of all, I will talk about the transformer architecture, because vision transformer utilizes the encoder transformer architecture. So first we start with some inputs, for example any string of text like the cat sat on the mat, and we have to convert this sequence of text into tokens, and this process is called tokenization. So the process of converting a string of text into tokens is referred to as tokenization. And then we have to map these tokens into token IDs. We have to map them into token IDs. Then we will pass these token IDs as inputs to input embedding layer, and then it will map these token IDs into high dimensional dense vectors. And then we will add positional encoding. Since transformers have no sense of built-in order or built-in positional encoding, we have to add this positional information to preserve the contextual information and to preserve the order information. So we add positional encoding to the input embedding. Then after we combine these two things, we pass them to a transformer block, which consists of a multi-head attention layer. Then we have to apply add and normalization layer. Add is the residual connection which adds the raw input before the multi-head attention to the combines it with the output of multi-head attention, and then normalize it using a norm layer. Then we pass the output of the add and normalization layer to feed forward layer. This feed forward layer will further fine tunes the representation into more fine-grained patterns, and this feed forward layer will discover more intricate patterns. Then we add the output of this add and norm before the feed forward. We do some residual connection and add it to the output of the feed forward. Then we have to normalize the output using a norm layer. After we finished the encoder block, we pass them to a decoder block. This decoder block is essential when you have some LLM model, but in this case the vision transformer doesn't utilize any decoder block. But in the decoder block you will apply some steps like masked multi-head attention, add and normalization. The same idea, we have some residual connection, and then multi-head attention, add a norm, then feed forward, and then add a norm, and then lastly you will use a linear layer to output some logits. Then we convert these logits into probabilities using the softmax function, and then we will output probabilities, as you can see in here. But in the vision transformer we just use an encoder block. In this image we have a step-by-step explanation of vision transformer architecture. As you can see, the first step is we start with an image, and then we have to convert or segment this image into patches. Why? Because this process is equivalent to the process of tokenization in NLP models. In NLP models we have to segment a sequence of text into tokens using a tokenization process. And this step is equal to that step. We have to segment the image into patches. We have to convert this image into small fixed size patches, and you define the patch size, whether it was 4x4 or 16x16 or any other patch size, whatever you choose. And then after we have segmented or splitted or sliced our image into patches, we have to flatten these patches. Why do we have to flatten these patches? Because the patch is a 3 or 16 by 16 by 3 channels. We have to flatten these, okay? So when you slice an image here, we start with an input image, for example 224 by 224 by 3 channels. This image is divided into fixed size batches, for example 16 by 16. This converts the image into a sequence of small flattened grids, and then we have to flatten these batches into vectors, because the transformer architecture only deals with 1D data, with one-dimensional data. So we have to flatten them, to flatten these batches to get 1D vectors. So flattened batches like this, we have just a column vector. And then we pass these vectors to the embedding layer to map these batches or vectors into high dimensional dense vectors. And then we add positional embeddings to preserve the order of the batches. So if you want to preserve the order or the order of the batches, you have to add positional embeddings in order to encode the positional information. Then we add a CLS token. CLS token is a special learnable token or vector that represents the whole image, and this CLS token will be used for classification. The output of this CLS token will be used later on for classification. And here, as you can see, we also add CLS token, the batch token, and the batch embedding, and then we feed this to the transformer encoder layers. The transformer encoder layers, if you notice here, transformer encoder, as we have explained earlier, the encoder consists of a multi-head attention, add a norm layer, and then we pass the output of the add a norm to the feed forward layer to further discover more hidden patterns, and then we pass it to an add a norm layer. So this is the architecture for an encoder block in transformer. So we do those same steps in here, we do them in here in the transformer encoder layers, and then we will pass the output of this transformer to the classification head to classify it into the predefined classes. For example, in this case, we are training the model on Cypher 10, so we classify them into 10 classes, whether it was airplane, automobile, frog, cat, horse, or whatever it was. It will output one logit or one probability value for each class, and then we will choose the highest probability or the highest logit using the argmax function to choose the predicted class. And also we have here a wonderful image that compares between NLP transformer and vision transformer. For NLP transformer, we refer to the segments of text as tokens. So the terminology here in NLP uses the word tokens. But in this vision transformer architecture, we will not refer to the segments of images, to the sub-segments of images as tokens. Instead, we refer to them as batches. So each sub-image or each sub fixed size small image, we will refer to it as batches. Here, if you can see, when we convert words or subwords in text, when we split the text into words or subwords, we refer to them as tokens. But when we split an image or slice an image into small fixed size batches, in Vision Transformer, we call the sub images as batches. Also, token IDs, we refer to the IDs that's mapped to each token. We refer to them as token IDs in NLP Transformer, but in the case of Vision Transformer, we refer to them as batch indices. So we map each token to an ID. For example, the cat is nice. We map the to 0, cat to 1, is to 2, nice to 3. But for batch embedding, we map each segment of the image, we map it to an index. For example, the top left corner, we map it to 0. The top right corner, we map it to 1. The bottom left corner, we map it to 2. And then the bottom right corner, we map it to 3. So converts tokens, explanation here, converts token or batch index, or here, each batch can be indexed like tokens. So each batch could be indexed like tokens. Then we pass these indexes numbers into a token embedding or embedding layer. Why? Because we want to represent them in high dimensional dense vectors. So for NLP, we call them token embeddings, or we refer to them as token embeddings, but in Vision Transformer, we refer to them as batch embedding. And remember, we have to flatten these batches. So converts token or batch index into dense vectors via learned projection. Then, as we have mentioned earlier, Transformer doesn't have any built-in functionality to understand the sequence or order. So we have to add positional embedding. Positional embedding is crucial if you want to keep the order or keep the position of each batch. So add positional embedding adds location information for sequence or order, or in the case of image, adds spatial structure. For the CLS token, we refer to it in NLP as CLS token, but in Vision Transformer, we also use CLS token, which is a special token to summarize sequence or image. Sequence, in the case of NLP, we call it sequence, but in Vision Transformer, we use image. So, special token to summarize or to represent the entire or whole sequence or image used for classification. We use the output of CLS token for classification to classify into some predefined classes. Encoder input sequence. So in NLP Transformer, we name the encoder as encoder input sequence, but for the Vision Transformer, we call it embedded batch sequence. So input to Transformer, the input that goes into the Transformer are tokens plus positional embedding or batches plus positional info. So the input that goes into the Transformer here, this Transformer encoder, is the inputs, which is image batches, small fixed size batches, plus positional info. Okay, so we combine these two things and then input them to the Transformer block, and the Transformer will use the multi-height attention to attend and focus on the important pixels and the significant pixels, and then it will learn it will learn to classify into different 10 classes. So here, input to Transformer equals tokens plus positional encoding, or in the case of images, we will have batches. Instead of tokens, we will have batches plus positional info. Transformer encoder layer or layers, Transformer encoders, the same terminology we use for NLP or Vision. Vision Transformer utilizes the same architecture for Transformer encoder layers. So explanation here, identical architecture for modeling dependencies. So in the Vision Transformer, we utilize the same architecture for encoder block, the same as NLP. We utilize it or use it in the Vision Transformer. So identical architecture for modeling dependencies. NLP Transformer output token representation. In NLP, we call it output token representation, but in Vision Transformer, we refer to it as CLS token representation. So as we said before, the output of the CLS token we will use to classify, will be used for classification. So we call it CLS token representation. The explanation here, used to generate final prediction. For example, class table. For example, horse or cat, frog. Last, we have softmax layer. This softmax layer we will use to output probabilities, and then we will choose the class with the highest probability. In NLP Transformer, we call it softmax layer. But in Vision Transformer, we use something called classification head, which is a multi-layer perceptron plus softmax. If you scroll up here in this image, after we have done the Transformer encoder layers, we take the output of the Transformer and pass it to the classification head. This classification head is nothing but a multi-layer perceptron plus softmax layer. So the purpose of classification head, which is multi-layer perceptron plus softmax, converts final output to class probabilities. And here we have a step-by-step Vision Transformer pipeline which takes the images into batches. First of all, we convert image into batches. So the input image, for example, the size or the height of it, 224 by the width, 224 by 3 channels. But remember, in Pytorch, we start with 3 channels, then the height, then the width. This image will be divided into fixed size batches, for example 16 by 16. But in this project we will use the batch size as 4 by 4. Here we set the batch size as 4, so we divide the image into 4 by 4 fixed size batches. And then the second step is converting the image into a sequence of small flattened grids. As we mentioned earlier, the transformer encoder deals with data in one-dimensional sequence, or deals with 1D data. It can't handle 2D data like convolution networks. So we have to flatten these batches. Then we will apply batch embedding. Why? To convert them into high-dimensional dense vectors. And then each batch is flattened into a vector and passed through a linear projection layer. And an important note here, the embedding layer used in Vision Transformer is a linear layer, so not an embedding layer as in NLP. In NLP, we use an embedding layer, but here we use a linear projection layer as an embedding layer to embed it. So we use a linear projection layer to embed it into a fixed length vector, like word embeddings in NLP. And then we have to add positional embeddings. We have to protect the sequence or the order of the batches in order to build context about the object inside the image. And then, since transformers have no built-in sense of order, positional embeddings are added to each batch embedding to preserve spatial information. Then, as we mentioned earlier, we add a CLS token, or we apply CLS token. Why? This CLS token will represent the entire image features, which is a special learnable token, and it is prepended to the sequence. Its output after the transformer will represent the whole image, and the output is used for classification. Then we apply the normal transformer encoder layers, multi-head attention, add a norm, feed forward, add a norm, and then the sequence will be like this: batch embeddings plus CLS plus positional encoding. The sum of this batch embedding plus CLS plus positional embedding will be fed into standard transformer encoder layers, which are multi-head attention or multi-head self-attention, add a norm, feed forward into work, and then add the norm, and then finally classification head to classify into the classes or the predefined classes. The final hidden state of the CLS token is passed through a classification layer, typically an multi-layer perceptron, to produce the predefined image class. So now I think this is enough for the theoretical concepts about Vision Transformer. Now we will move on to the practical side and build an end-to-end project, starting from importing the libraries and then getting the CIFAR 10 dataset, and then preparing the data further by converting them into batches, and then building the Vision Transformer components, building a multi-layer perceptron, building a classification head, and so on, and then train the model for 10 epochs, and then we will make predictions, and then we will fine-tune the data by doing some data augmentation techniques like random horizontal flip and so many other augmentations, and then we will train the model again, and finally we'll make predictions using the model. So see you in the practical section. We'll build Vision Transformer on CIFAR 10 dataset using Pytorch and from scratch. If you don't know what CIFAR 10 dataset is, you can search in Google CIFAR 10 dataset, and if you choose the first result, it will redirect you to this website. So this is the official website for CIFAR 10 dataset. As you can see in here, the CIFAR 10 dataset consists of 60,000 images, each 32 by 32, so the height of the image is 32 and the width of the image is 32, and they are color images in 10 classes. So color images meaning they have 3 color channels. They have red channel, green channel, and blue channel, divided into 10 classes. So we have 10 classes. We have airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. We will try to model this dataset using a vision transformer architecture, and we will build it in this video. So let's dive in. The first step, we need to import required libraries. Well, of course, we need to connect to the runtime. So we have to go to runtime, then change runtime type and choose T for GPU, for example, and then connect. Now we will wait until the runtime connects. As you can see, initializing. Now it's connected. Now we can start to code. So the first step is we need to import Torch. We need to get the Torch library. So import Pytorch, and then import torch.nn as nn. nn is a sub-module inside Torch that contains lots of layers, lots of loss functions, and so on. Import torch.nn.functional as f. Also we need import torch.optim. So optim package, optim is a package inside Torch that contains lots of optimizers and many optimizers like Adam optimizer and SGD for stochastic gradient descent. So as optim, and then from torch.utils.data import DataLoader. DataLoader is a very helpful class that will convert our dataset, our Pytorch dataset, into batches. So we need to batchify our dataset, and then from torch vision import datasets. We will need datasets library to get a dataset, comma transforms. Also we need some transformations to apply them on our images. Import numpy as np. We will also need numpy. Import random. We will use random to generate random indexes to visualize some images randomly, and then import matplotlib.pyplot as plt, and matplotlib is fundamental for visualizing. Now let's run this cell. If you want to check the versions, to check that we have got our libraries ready to go, torch.__version to check what is the version of Torch. We have 2.6.0 and the CUDA version is 12.4. Also Torch vision .version. These are just to make sure that we have our libraries ready to go. I have misspelled Torch vision .version. Torch vision is not defined. We need to import Torch vision. So import Torch vision, because we haven't imported Torch vision. We have imported datasets and transforms from inside our Torch vision. And then we will run our Torch vision.version. As you can see, yeah, now we have 0.21.0 plus CUDA version 12.4. Now we have imported our required libraries or our required tools to build this project. The next step is we need to set device agnostic code. So set device, let's put a comment in here, set up device agnostic code. So to set our device agnostic code, we will define the variable device equals CUDA, string CUDA, if torch.CUDA.is available, else CPU. So now, right now, we are connected to a GPU. If you hover over this section, you'll see connected to Python 3, Google Compute Engine backend, and we do have a GPU. So we have a GPU connected. If you want to check that, if you want to make sure that you have a GPU ready to go, you can type in a exclamation mark, then NVIDIA-SMI, and you will get a report that shows that yes, we do have Tesla T4 GPU. And also you can go torch.cuda.isAvailable, and this will return a boolean indicating if CUDA is currently available. If it's available, it will return true. If otherwise, it will return false. As you can see, it returns true. Yes, we do have a CUDA. Now this variable will contain the device CUDA. Now, yes, we do have CUDA, and then we can print a pretty print statement here. Print using device, which is device, and then we are using device CUDA, as you can see in here. Now we can move on to the next step. The next step is we have to set the seed. So set the seed. Let's go torch.manualSeed 42. So manual seed just sets the seed in Pytorch library, and then torch.cuda. We also need to set the CUDA, the manual seed, manual seed as 42. Here you can see set the seed for generating random numbers for the current GPU device. And then we can go random.seed as 42. With that being said, we have set our seeds correctly. Now we can move on to the next step, which is setting the hyperparameters. The first hyperparameter that we're going to use is batch size. So we need to set the batch size as 128, and then the next hyperparameter epochs equals 10. Well, we as machine learning engineers or as deep learning engineers can set these hyperparameters to whatever we want, So you can experiment, you can try 20 epochs, you can try 50 epochs, and so on. You can try the batch size, for example, 256. So the multiples of 8 are commonly used for batch size and for these type of things, because multiple of 8s are compatible with the computing for the GPU and devices. So you can use any number in here. In this case, I will use 128, epochs as 10. And then learning rate is another hyperparameter that you can play around with. I'm going to try 3e-4, which is if you want the other version to write this number, it will be 0.0003, okay? And then we will set our batch underscore size equals 4, because we will segment our images into patches, and these patches are going to be like tokens. It's the equivalent process when you have some sequence of text and you want to segment it into tokens. Here we're going to segment or split our images into patches, and we're going to define the batch size as 4, and then the number of classes, num underscore classes. Well, we are dealing with Cypher 10 dataset, and we have 10 classes, as you can see in here. We have 10 classes, so the num of classes equals 10. Image size, the default image size for Cypher 10, you can see in here. Cypher 10 dataset contains 60,000 images, each 32 by 32. So we're going to set our image size as 32. And then the number of channels. Channels are the color channels. These images are color images, so they have 3 color channels. We're gonna set channels as 3, and then embed dimension, embed.dim. I'm going to set it as 500 or 256. Number of heads for multi-head attention, num of heads equals 8, and then depth, the depth equals 6. We will have 6 transformer blocks, and then MLP, multi-layer perceptron underscore dimension equals 512. And then lastly, the drop rate, I'm going to set it as 0.1. Let's run that. Now we have set our hyperparameters. Let's move on to the next section. Now we will define our image transformations operations. So let's go ahead and define image transformations. The first thing, we will define a variable called transform equals, first of all, we will try to build a model without data augmentation, and then we will build a model or another model with some data augmentation techniques. So let's go transforms dot compose. I'm going to compose some operations in here. For example, the first operation as transforms dot to tensor. We have to convert our images into tensors in order to be able to pass them to a model. So we can't deal with images in their pure format. We need to convert or turn our images into tensors, into numbers, into some numerical format, into some numerical encoding to be able to deal with them inside the model. So to tensor, okay, and then transforms dot normalize. We have to normalize our images. The mean, we're going to set the mean as 0.5, and also we will set the standard deviation as 0.5. Why? Because we have to normalize our images for some reasons. The first reason, it helps the model to converge faster, and also the second reason helps to make the numerical computations stable. So numerical stability. These are some of the reasons why we will have to normalize our images, because when you make the mean 0.5 and the standard deviation as 0.5, it will be easier to deal with from the model, by the model. The next step, which is we have to get a dataset. So 6, getting a dataset. Well, this dataset is Cypher 10. So let's go ahead and create a variable called train data set equals datasets library dot the class Cypher 10. So we have this Cypher 10 class inside the datasets library inside Pytorch. If you go torch vision datasets, we have many different datasets that we can choose from. We have here Cypher 10 dataset, and this class takes from me the root. So where do you want to download this data? And then it takes from me also train, whether we want the training version or the testing version. Transform, what transformations do you want to apply on the images? And then target transform, and then lastly download, yes or true. So let's pass these parameters. The first parameter root equals data. It will create a folder or directory called data into here. And then the second parameter as train equals true. Yes, we want the training version, comma, download. Do you want to download it? Yes, we do. Transform, what kind of transformations do you want to apply? Well, we will apply these transformations, which is stored in this variable transform. So let's pass in here transform. And now we can run that. It's now getting our data. It's now loading, as you can see. The progress bar is progressing, and we have 170 megabytes total size of data. It's now loading the dataset into this folder. Now it's finished. It has loaded all of our data. Now let's do the same thing, but for our testing data. So let's go ahead and create a variable test underscore dataset equals datasets library that we have imported earlier from Torch Vision dot the class Cypher 10 class, and then pass into here root as data, comma train. And this time we will pass false. Why? Because we want the testing dataset or the testing version from Cypher 10. And then download, yes we do. Transform, we will apply the same set of transformations that we have applied in our train data. So pass transform. And let's run that. Now we have gotten our datasets ready to go. We can check that by going train dataset. As you can see, we have a dataset or Pytorch dataset object, which is Cypher 10. Number of data points, we have 50,000 images. Root location, it's stored in data directory. Split, train, standard transform. The transformations that we have applied are just two simple transformations. The first is to tensor, to convert images into tensors, and the second is normalize, to normalize our images. And also you can check the same thing for our test data. Let's go test data set. The same thing, but we have number of data points here. We have just 10,000 images in the testing set. Also, we can check the length of train dataset, which is 50,000, and the length of test dataset as 10,000. Now let's move on to the next step, which is building or converting these datasets into data loaders. Now we will batchify our data. So step 7, I believe it's 7 now. Yes, we're up to 7. So step 7, converting our data sets into data loaders. Why would we do this? Well, for two main reasons. So right now our data is in the form of Pytorch datasets, and we need to convert these datasets into data loaders. So recall that a data loader turns our data into batches or mini batches. So why would we do this? Well, for two main reasons. The first reason, it's more computationally efficient. It is more computationally efficient because as in your computing hardware may not be able to look at or to store in memory, in other words, to store in memory at 50,000 images in one hit. So what do? Since that our memory wouldn't fit our 50,000 images, we will try to divide this dataset into batches. So we will break this dataset into batches or into mini batches to be more computationally efficient. So we can break it into 128 images at a time. So the batch size of size 128. So this is the first reason, because your computing hardware may not be able to look at or to store or to process all 50,000 images in one hit. So we need to break it down or to divide this dataset into groups or subgroups, each group containing 128 images. The second reason, it gives our neural network more chances to update its gradients per epoch. Well, rather than just one update per epoch, we will have as many batches we have updates in each epoch. So after each batch, the model will update its weights and its parameters, rather than after the model sees all 50,000 images in one hit and then updates its gradients or its weights. So we will have more chances to update the gradients of the network per epoch. So we will have many updates per epoch rather than just one update per one epoch. So let's do that. The first thing, we will define a variable called train data loader or train loader equals the class data loader that we have imported earlier. Data loader. This class takes from me dataset and the batch size and shuffle yes or no. So let's pass in here dataset equals our train dataset, comma, the batch size. So batch, how many samples do you want in each batch? We have defined it earlier. If you recall, we have a variable called batch underscore size. It contains 128. So let's pass that into here, batch underscore size. The last step is shuffle. Do you want to shuffle it, yes or no? In this case, yes, we will shuffle the training data, but for the testing data, we will not shuffle it. Why? It's considered a best practice to not shuffle the test data. So dataset equals test dataset, comma, batch size. How many samples do you have in each batch? In this case, we will define batch underscore size, comma, then shuffle. Do you want to shuffle it? No, we don't. False. Now we can check out what we've created. So let's check out what we've created just to make sure that we are going in the right path. Print f-string DataLoaders. We will pass in here train loader, comma, test loader, and then print. We will print the length of train loader. So how many batches do we have in the train loader? By going the length of train underscore loader, we have this number of batches. Each batch contains this number of batches of batch size, and then print f-string length of test loader as length of test underscore loader, and we have this number of batches. Each batch contain this amount of items or examples, Now let's run that. As you can see, we have DataLoader torch.utils.data.dataloader object stored at this location, and we also have the same thing for the test data. But the interesting thing in here that we have length of train loader, we have 391 batches of 128. So each batch contains 128 samples. If you multiply that by the number of batches, which is 391, we will have roundly approximately 50,000 images. Well, why do we have more images in here? Well, this number is rounded, so the last batch doesn't contain 128 images. It contains less because it tries to fit those images into batches. So this number is rounded. Maybe the correct number is, for example, 390.5. We will have somewhat. If you divide 50,000 by the batch size, which is 108, the right number is 390 point this. So if you try to multiply this number here, we will get exactly 50,000 images. But it will try to fit in the last batch. How many images do we have remaining? The same thing for the test loader. Length of test loader, we have 79 batches. Each batch contains 128 images. So that, with that being said, now we have divided our data sets into batches, or we have batchified our data. We can move on to the next step, which is building our VIT components. So building VIT, which is vision transformer. Now we're up to section 8, building vision transformer model from scratch. Now the first component that we need to create, we need to go class and then batch embedding. Why batch embedding? Because as we said, we need to split our images into patches, into segments, and this process is equivalent in text. If you build an LLM model, you will divide a sequence of text into tokens. So here we are dealing with images, so we need to split our images into patches, and each patch, so the patch size, if you recall, the batch underscore size is of size 4. Now we will define some parameters in here. So this model will, or this class will inherit from nn.module, and then we will define our init method. Init, it takes from me self, also it takes from me image size. So what is the image size? Comma, it takes from me batch size. What is the batch size? And then in channels, how many channels do we want to input? Comma, embed size, embed underscore dimension, and then we will define our super dot underscore init to run our supers module inits inside the init of this child class, which is batch embedding. The first step is we'll create a property called batch underscore size equals batch size, batch underscore size, and then self dot proj meaning the projection equals nn dot convolution 2d. We'll define a convolution 2d layer. This layer will take from me in channels equals, so how many number of channels do you want to input? In this case, we'll pass the same as in channels as this parameter, in underscore channels, comma, out channels. How many out channels do you want to output? In this case, we will define it as this parameter, which is embed underscore dimension, the same as the number passed to this parameter embedding dimension, comma, kernel size. So what is the kernel size that you want to apply? The kernel is the feature detector. It will convolve over the image, across the image, and extract the features, spatial features. We will pass it as the batch size, batch underscore size. So we will define the kernel size the same as the batch size, comma, stride, the steps, or how many steps, how many pixels do you want to move over in each step. In this case, we'll define it as the batch size in order to segment our image into multiple batches to be able to process it by the transformer model. And then self dot, we need to define the num batches. So num underscore batches equals image size divided by, using 2 slashes to get an integer division, divided by the batch size, and then raised to the power 2. So this equation, we are dividing our image size, dividing it by the batch size, whatever it was, for example 4, and then raising it to the power of 2. Self.cls token. So the classification token is a special vector that we want to learn, or we want to train in the training in the training phase, equals nn.parameter. So we will use the parameter class from inside nn to create a parameter that will be updated in the training phase, equals torch.randin. We will initialize the values for the weights, or the weights of the classification token. We will initialize it randomly. An important rule in machine learning, we always start the weights or biases randomly, and then in the training phase, the optimizer will hopefully try to optimize or fine-tune or update these weights. Torch.randin 1, 1, and then comma embed them. And then also we will define the position embedding. So position encoding will try, or position embedding will try to reserve the positional information, or the positional information to protect it from being lost, equals nn.parameter. We'll create a parameter that will be defined as torch.randin, generate some random integers, 1, 1, and then plus number of batches, which is this variable num underscore batches, and then we will pass into here embed underscore dimension. Now we have defined our model setup, or our model components. We have a batch size component, we have a projection layer component, and we have CLS token. As we said, CLS is a classification token, an important or special vector or special set of weights that we want to train or update, and position embedding also to preserve the positional information or positional content within the image, because we have splitted our image into batches. The next step is the def forward. We need to define a forward method, takes from me self, x. X will define it as torch.tensor. So it's a tensor. X is the data that is passed through this model. B equals x.size, and then pass 0. So this step is, we're just the dimension for which to retrieve the size. We want to retrieve the size at index 0 for x, and store it in B. and then x equals self dot projection. We will call this projection, call this convolution 2D layer, and pass to it this x variable or x parameter that we have passed into this forward method, and then so this as b comma e comma h divided by the batch size, so the height divided by the batch size, comma width divided by the batch size. The next step is x equals x dot flatten. We need to flatten our x data, and then pass in here 2, the dimension as 2. Dot transpose, we will have to transpose it into 1 comma 8. Why? To make sure that the shapes align. So it will become now as this, b comma n comma e. And then cls underscore token variable equals self dot cls underscore token, cls underscore token attribute, and then pass into here the b variable, which is the size at index 0 dot, and then torch dot or self dot cls token pass b comma -1 comma -1. X equals torch dot concatenate. We will need to concatenate using the cat function, so concatenates the given sequence of tensors, and then we will pass in here cls token and concatenate the cls token with the x variable, and then specify dimension as 1. X equals x plus self dot position embedding, and then we will add, after we have concatenated our cls token and our x data, we will add the position embedding to preserve the position data, and then return, and then lastly return x. If you run that now in that syntax error, method can't object. Well, invalid syntax. Why? Torch. We have forgotten to put an equal sign, a classic error. No problem. Now let's run again, and as you can see, we have run the cell and it's successfully run. The next step is to define the multi-layer perceptron class. So let's go ahead. Class multi-layer perceptron for short. Its subclass is nn.module. nn.module is an important component in Pytorch. Almost all your models should also subclass this class. So module is a base class for all neural network modules, and your models should also subclass this class. So all your models in Pytorch, almost all Pytorch models, should subclass the module class. And then the first step is def underscore underscore init underscore underscore. It takes from me self, also, or self is the keyword to make this method, to make this function a method in OOP. The next thing is we need to pass into here in features. So how many features do we need to have in features, comma. Also it takes from me hidden features, how many hidden features or hidden units, comma, drop rate. Also takes from me what is the dropout rate. Let's call super.init to run the init method of the module inside the init of this child class, multi-layer perceptron. The next step is self.fc1, so fully connected layer. Another name for the linear layer is fully connected. Whenever you hear someone refer to a linear layer or to a layer as fully connected, it's the same as a linear layer. So fully connected 1 equals nn.linear. We'll define a linear layer equals in features. How many in features do we have? The same as this parameter. We will pass in here in underscore features, comma, hidden features as the out features. So out underscore features equals the number of hidden features, hidden underscore features. And then the next layer is also, we'll create another fully connected layer using self.fc2. So fully connected 2 equals nn.linear. We'll define a linear layer that will take from me in features equals, well, this layer outputs hidden features, the number of outputs will equal the number of hidden features, and then this layer must receive the same number of inputs as the data that was outputted by this layer. So how many outputs do we have from this layer? This layer should receive equals, we have to specify in here as hidden features. We must specify it as hidden features, otherwise Pytorch will throw an error. And then we'll define out features equals the same as our in features. The last layer, or the last component inside this init method, which is for multi-layer perceptron, we'll define it as self.dropout. Dropout layer is a layer that zeroes out some neurons in order to prevent overfitting. So let's go ahead and then dropout layer. Dropout, if you want to read about it, you can go and then dropout, and you can search about dropout and what are the benefits gained from using a dropout layer. During training, randomly zeroes some of the elements of the input tensor with probability of p. So dropout takes from me a probability. What is the probability that you want to specify? And this probability will define how many neurons that the dropout layer will zero. So the zeroed elements are chosen independently for each forward call and are sampled from a Bernoulli distribution. Each channel will be zeroed out independently on every forward call, and so on. So we need to pass in a probability of an element to be zeroed. Default is 0.5, but we will define it in this case as the dropout rate that we will pass into here, dropout rate. And then we have finished our init method. We can move on to the def forward method. So def and then forward method. So forward method specifies the forward competition to be done when this class is called, or when a model is being instantiated from this class. So let's pass in here self, comma, x. The first step is x equals self.dropout, which is this component. We will apply some dropout and then call our f, which is the functional class that we have imported from Pytorch. So we have torch.nn.functional. We have imported it earlier in this notebook, if you recall, from import torch.nn.functional as f for short. So we will use this f class and then pass into here f.gelu. So gelu is an activation function, gelu, and then pass in here self.fc1, which is fully connected one, and pass to it 1x. So what we are doing here is we are taking our input data that is passed to this model and passing this data to a fully connected layer that we have created into here, which is a linear layer, and then taking the output of this linear layer and passing it to a gelu function, and taking the output of this gelu function and passing it to a dropout layer to zero some elements. The same thing, x equals, now we will overwrite x, we will overcast x to be equal self. Also we will apply another dropout layer, self.dropout. We want to drop out some layers and then pass here self.fully connected to. Now we want to use our second linear layer, our second fully connected layer, by calling fc2 and passing in here x. So we want to take x, which is the output of this dropout layer, and pass it to another fully connected layer, and then passing the output of the fully connected layer to a dropout layer to prevent overfitting, and then return x. Now we have finished defining our multi-layer perceptron class. Let's move on to the third component, which is building a transformer encoder layer. So let's go ahead, class, and then name it as transformer encoder layer. This class should also subclass encoder.module. As we said, your models should always subclass encoder.module. And then define an init initializer method. It takes from me embed dimension, comma, also number of heads, num_heads. How many heads do you want to use? and then MLP dimension, comma, drop rate. So what is the drop rate that you want to use? We need to call super and then parentheses dot underscore init, then parentheses, and then we need to define self dot norm 1, which is a normalization layer, equals nn dot layer norm. Layer norm is a normalization layer that we have to use in here, and then pass into here embed dimension. The second component is attention. We need to define or create an attention layer by going nn dot multi head attention. So this is a layer inside Pytorch. It takes from me embed dimension. How many embed dimension do you want to use? We will pass it as embed dimension, comma, num underscore heads, the same as we passed into this parameter, number of heads, comma, the dropout rate equals dropout rate or drop rate into here, comma, batch first. So how many, what is the batch first equals true, yes, or true. So pass into here, batch first, it's a boolean, we have to set it as true. The second layer is another normalization layer, norm 2, we have norm 1 and also have norm 2, which is the second normalization layer, equals nn dot layer norm, and then pass into here embed underscore dimension. Then we will define a multi-layer perceptron layer as MLP. So we will call that class, we will call this class MLP and use it inside this another class, and pass into here embed dimension, comma, MLP underscore dimension, and then drop underscore rate. Now after this init method, we will define another forward method which specifies the forward computation for this class or for this model. We'll define here self comma x. As we said, x will be the data that is passed to this model. The first thing, x equals x, we will take x as it is and then add or put a add sign here. Then we will call this attention layer by going self.attention and then pass into here self.norm1. So we will apply our normalization layer, our first normalization layer. We will apply it here and then pass to it the x parameter, comma, self.norm2. Also we will use our second normalization layer and pass to it our x, comma, self.normalization1, and then pass into here x at index 0. And then we will go x equals x plus self.multilayer perceptron and pass into here self.normalization2 layer, was our second normalization layer, and then pass into here x. Well, in this first x assignment, we will use normalization 1. So I have mistyped normalization 2. We need to use norm 1 layer in the first call of attention, and then in the second x equals here x plus self.multilayer perceptron, and then pass into here the second normalization layer and pass to it x. Return x. Now we have to return x. The next step is we need to create a class called vision transformer to combine all of these components. So class, and then we will call it vision transformer. This class will take from subclass init module, and then it will define init as usual. The first thing it takes from me image underscore size, comma, it takes from me also batch size. So what is the batch size, comma, in channels, how many channels do you want to use, comma, num underscore classes, how many classes do you want to use, comma, embed underscore dimension, what is the embed dimension you want to use, comma, depth, the depth of the block, comma, num underscore heads, and also we need to pass in multi-layer perceptron comma dimension, comma the drop rate. So these are all of the inputs that we have to pass into when we want to create a vision transformer instance. The first thing, we have to call super.init by going underscore init underscore. This is necessary whenever you subclass an input module. And then self.batch underscore embed. So in this property, we will call our batch embedding class that we have created into here, our batch embedding class, and pass to it the image size, the batch size, in channels, and embed underscore dimension. So let's do that. Call batch embedding. This class takes from me the image size, image underscore size, and then takes from me also, or receives from me, the batch underscore size. Also, how many channels do you want to use? Equals in channels, comma embed underscore dim. The second step is we have to define an encoder by going self.encoder equals nn.sequential class. This sequential class will define some components, and the data, when the data goes through the sequential class, it will go through it layer by layer. So it will go sequentially, layer by layer. The first layer into here, which is transformer encoder layer, this layer we have to pass into here embed underscore dimension, comma the number of heads, as you can see in here, num underscore heads as num underscore heads, and then comma we have to pass multi-layer perceptron underscore dimension, comma the drop rate as drop rate. And then we will put into here, we have to pass a list here to do some list comprehension operation into here. And then for underscore, we want to discard this variable, we don't want to use it. So for underscore in range of depth. So however many depths that we have specified into here, we will loop through this list and create transformer encoder layer. So if you have specified depth as 10, we will have 10 transformer encoder layers. If you have specified depth as 6, we'll have 6 transformer blocks into here. So this is an efficient way to loop through a layer and duplicate this layer however many times you want to duplicate it. Self.norm, we have to specify a normalization layer by going nn.layer norm and then pass embed underscore dimension. Self.head, the head layer equals nn.linear. We will create a linear layer or dense layer by going embed underscore dimension, comma, and then specify num of classes. This head layer will classify. It will act as the classifier. It's a linear layer that will take however many embed dimensions we have, and then outputs 10 probabilities or 10 logits for each class a logit to choose the highest logit and predict that the output is the same as the highest output that have or that has the highest probability or the highest logit value. So we have to specify the second parameter as num underscore classes to get however many logits we have for each class. So if you have 10 classes, we will have 10 logits. And then specify def forward, the forward computation, by going self, comma x equals, we have to call in here self.batch embed, batch underscore embed. This batch embed layer, we will pass through it the x, and then x equals self.encoder. We have to call encoder. This encoder is a sequential model that contains however or how many depths we specify into here. We will have the same number as or of transformer encoder layer. So by going or by passing into here x and then x equals self.norm, we have to normalize our outputs by using this norm layer, which is a layer norm and we have to pass it embed underscore dimension. So specify in here x CLS underscore token, the classification token equals x, and then do some indexing in here, comma 0. So we have to specify colon, comma 0. Lastly, return self.head. We'll apply our head layer, which is a simple linear layer, and it will output 10 loaders because we have 10 classes. So for each class, we'll output one loader, and then pass into here classification underscore token. Now we have created our vision transformer class successfully, and all of the components now are ready to go. We have to instantiate our model, or to build an instance, or to create an instance from our vision transformer class. So the first step is we have to put a comment here and instantiate model. We have to instantiate a model, a new model, by going model variable equals the name of this class, which is vision transformer. So let's pass into here vision transformer, and this class takes batch size, image size, in channels, num classes, embed them. So it takes a fair bit of parameters that we have to pass into here. So bear with me until we pass all of these parameters. The first parameter is image size, comma. The second parameter is batch size. We have to pass all of these parameters, and then channels. We have to pass in channels. Also num classes, comma. You have to pass into here also embed dimension, comma, the depth. So we have depth. I believe the depth was 6. If we go depth, we have 6 depths. Yeah, 6. So we have 6 transformer blocks. Remember, we are looping through the depth. So we will create 6 transformer encoder layers, each with embed dimension and number of heads and MLP dimension and drop rate parameters passed into it. So we have to pass these things in order, and then num underscore heads, the number of heads, comma, MLP underscore dimension, comma, drop rate. So now we have specified all of our parameters successfully: image size, batch size, channels, num classes, embed dimension, depth, num heads, MLP dem, comma, drop rate. These have to go in order. We have to pass them in order. And then dot to device, we have to move our model to the target device, because now our current device is CUDA. So you have to pass our model, or we have to move or send our model to the CUDA device by going to device. So now after we instantiated our model, we got an error. And this error says that make underscore subclass argument required grad position 3 must be boolean, not integer. The mistake that we have done here is in the class of batch embedding, specifically in the position embed attribute, we have passed the embed dim parameter outside of this parenthesis. So we need to include it inside the rand-end function instead of passing it outside of the rand-end function. So let's run again, and then run all those cells again, and then let's try to instantiate the model. As you can see, the model now is instantiated correctly and successfully. If you want to visualize the model, you can go model, and this is the model architecture. As you can see, we have 6 transformer blocks. First of all, we have the first layer we have is a patch embedding layer, which is a convolution, and has a projection layer, which is a convolution 2D layer that has 3 input channels, red, green, and blue, and has 256 output dimensions. And the kernel size is 4,4, stride is 4,4, which is the batch size. Encoder is a sequential, and then contains 1 transformer encoder layer, 2nd transformer encoder layer, and then the 3rd transformer encoder layer, because we have looped over the depth, which is 6, and then 3 transformer encoder layer, and 1 transformer encode layer, which is 4, transformer encode layer 5, and then the last one, because we have started from the index 0, indexing start from 0, we have 6 transformer encoders, 0 to 5. So starting from 0 to 5 results in 6 transformer encoder layers. The next step now is we need to define a loss function and an optimizer. So the number of step now is step 9. We can go step 9, which is defining a loss function and optimizer. And an optimizer. So the loss function that we're going to use is cross entropy loss. We want to use cross entropy loss, so we can go criterion. Criterion is another word for loss function. Criterion equals nn.cross entropy loss. And then the optimizer is going to equal torch.optim.atom optimizer. Atom optimizer will take params or receives params. The parameters will be our model.parameters method. We will pass our parameters method and then put 2 parentheses. The second parameter is learning rate. The learning rate you can define as our previously defined hyperparameter, which is learning rate. Now we can run the cell, and as you can see, it's now instantiated correctly. You can view the criterion, which is cross entropy loss, and also the optimizer, Atom optimizer, and you can see that the AMS grad false, betas and capturable false, and so on and so on. These are some of the parameters that is passed to the Atom optimizer. You can see learning rate as 0.0003. Now we have to create a function to train our model. So let's go ahead and define that. Now the step is 10. Step 10, defining a training loop function. So to define a function in Python, we have to go def is short for define, def train, and then this function takes from me model, takes from me also a loader, comma, optimizer to use to optimize our model's weights and parameters, and then a criterion to compute the loss function when training the model. First, we have to set the module, set the mode of the model into training by going model.train. So we will pass a model in here, and then we will set the mode of this model into training mode using .train function. So this function set the module in training mode. The next step is we need to instantiate 2 variables, or to initialize 2 variables. The first one, total loss, for the total loss, comma, correct, the number of correct predictions equals 0, 0. So instantiate those variables as zeros. And then we will loop through for x, y. X are going to be a batch of images or a batch of photos, and y is going to be a batch of labels or targets. For x and y in loader, we will loop through the loader that we pass into here. So for x, y in loader, for each batch in our data loader, the first step is we need to move our data by going x, y, move our data into the target device. So x.to device, y.to device. So right now, you can recall that device is CUDA. So we want to load our data into the CUDA device by using this syntax, x.to device, y.to device. So this setup is important, moving or sending our data into the target device. Then we have to do optimizer.zeroGrad. We have to zero the gradients, or to reset the gradients, 0_grad function. Reset the gradients of all optimized torch sensors, important step in every training loop. And then we have to do the forward pass. So forward pass And remember that the forward pass, the model outputs raw logits. So we can go out equals model. We will use our model that we pass into here, and then use that model and then pass to it x. So we will pass a batch of images or a batch of pictures through the model, and then the model will compute on it, will do a forward pass, and then make predictions and store those predictions in here in this variable, which is out. And then the second step is we need to calculate the loss. So this loss will be per batch. So we will go loss equals criterion. We will use our criterion that we have created over here. Criterion equals NN cross entropy loss. Cross entropy loss is useful when training a multi-classification problem. So it's useful when training a classification problem with C classes. So if you have a multi-class classification problem, meaning in other words, you have more than 2 classes, you have 3 classes or more, you want to use cross entropy loss. But if you have just 2 classes, you have to use binary cross entropy. But in this case, we have to use cross entropy loss. And a quick pop-up here. What is the purpose of cross entropy loss? Cross entropy will measure how wrong our model is, or how wrong our model's predictions are. So cross entropy loss, we use this loss function to compute how wrong our model is, meaning how far the predictions from the actual results. And the optimizer, what is the purpose of the optimizer? The optimizer will update our model's parameters, to try and reduce the loss. So the optimizer will try and reduce the loss by optimizing the parameters or the weights. Now we will use our criterion to compute how far our model's predictions are from the actual outputs or from the truth outputs by passing the out. So we will compare the model's predictions, we will compare them to the ground truth, which is y. Y contains the labels or the truth labels. And then we have to perform back propagation to compute the gradients of the loss with respect to all of the weights and parameters in our model. So we can go loss.backward. And if you want to learn more about back propagation, you can go what is back propagation algorithm, and you will find a Wikipedia article on what is back propagation. You can read in here, in machine learning, back propagation is a gradient estimation method commonly used for training a neural network to compute its parameter updates. It's an efficient application of the chain rule to neural networks. Back propagation computes the gradient of a loss function with respect to the weights of the network for a single input-output example, and does so efficiently, computing the gradient one layer at a time, iterating backward from the last layer to avoid redundant calculations of intermediate terms in the chain rule. This can be derived through dynamic programming. So it is a powerful algorithm to train modern neural networks in deep learning. And then the fourth step is perform gradient descent algorithm by going optimizer.step. So this step function will perform a single optimization step, and in other words, this step function will also perform the gradient descent function. Now we will accumulate the loss by going total loss. So in each time we will accumulate the total loss, this variable instantiated as 0. We will add whatever loss we get in here. So we will add loss.item. We will get the item, or we want to get just the scalar item function. If you read here, it just returns the scalar value of the tensor. And then we will time that by x.size at index 0. Correct the number of correct predictions. We can calculate it using out.argmax at index, or we will specify the dimension as 1 to calculate the argmax. Argmax will return the index of the highest probability, or will return the index of the highest of the highest probability or highest logit. And then if it equals the real label, equals y, then dot sum, we will get the sum. So how many correct predictions, and then dot item to get the item, not the tensor. And then the last step is we will return total loss divided by length of data loader or loader dot dataset. Why we have to divide the total loss by the length of loader? Because we have accumulated the loss. Every batch we will accumulate it, or we will add it, we will increase the total loss, and then we have to normalize the loss. We have to scale the loss. So you have to scale the loss or normalize it. So normalization step to make the loss general across all batches by dividing whatever loss we get here on the length of DataLoader.dataset. Important step. And then the same thing with the correct. We have to divide the correct, divide by the length of loader.dataset attribute. Now we can run that. So now we have defined our train function, as you can see. Let's move on to defining our evaluate function by going ahead and defining evaluate. It takes from me model and loader. So model to evaluate it, and loader to evaluate the model on it. And then this function will take from me, first of all, we will have to define the model in eval mode by going model.eval. Eval set the module in evaluation mode. So eval set the mode of the model into evaluation. And then the next step is we have to define a function correct and initialize it as 0 equals 0 with torch.inference mode. We have to turn on inference mode to make predictions using the model for x, y. So for each batch of images and for each batch of labels in loader, we have to first of all move our x and y into the device or target device by going x.to device, y.to device. So we have to move x into the target device .to function device, and y.to send y or send the labels to the y to the device where the model lives. And then out equals model and then pass x. So we will use our model that we pass into here, our past model, and then pass to it our x, and then the model will make some predictions and store them in the out variable. And we have to calculate how many correct predictions the model has made by going correct plus equals, so accumulate on the correct variable or add to the correct variable, and then out.argmax, we will define or we will apply the argmax function on the out variable to get the index of the highest probability, and then specify the dimension as 1. If it equals y, then we will get the sum of this and get the item scalar from the tensor. And then we have to go outside of the for loop, also outside of the with torch inference mode here, and then return correct divided by the length of DataLoader.dataset. Length of loader, this variable dataset attribute, and then run the function. Now we have defined our train function to train the model to optimize the weights, and our evaluate function to evaluate the model and get the model accuracy or results. Now we can train our model. So we have to set a comment as training, and then train underscore accuracies equals an empty list, comma, or test accuracies, and then equals a list. You can do this syntax, or you can shorten it by going like this. You can put a comma, list, and then define this variable in the same line. So whatever syntax you choose, it depends on you, or it's up to you. Train accuracies, comma, test accuracies equals two empty lists. We want to initialize them to log our accuracies and to record our accuracies for training and for testing. So for epoch in range of epochs, we will loop through our epochs. How many epochs do we have? Currently, we have set our epochs as 10. So we have 10 epochs. We will loop 10 times. For epoch in range of epochs, for each epoch, the first thing, we will get a train loss, comma, train accuracy equals train. So we will call our train model, our train function. This train function will return a loss value and accuracy value. So train will take from me a model, a loader, optimizer, and criterion. A model to train it, a loader to train the model on it, optimizer to use to optimize the model's weights and the model's weights and parameters, and criterion to compute the criterion or loss function. So pass into here model, comma, loader, and then also we have to define optimizer or pass optimizer, and pass also criterion to get the loss in each step. The next step is test accuracy, and then call our evaluate model, our evaluate function. So evaluate function takes from me a model and a loader. We have to pass in here our model and our loader. Model, comma, loader. The loader here will be the test loader. The test underscore loader. And the same thing here, you have to pass train loader. We have forgotten to put train. Here we want to train the model on the train loader, and you have to test the model or evaluate it on the test underscore loader. So you have to notice these variables. We have train loader and we have test loader. And then we will append in the train accuracies list, we will append by using .append. We're going to append our train accuracy, which is this variable. So pass train underscore accuracy and append it to the train accuracies list. And the same thing goes for the test accuracies. Test accuracies .append, we will append our test accuracy variable, which is this. So in each loop or in each epoch, we will log the accuracy of the training and the accuracy for the testing. The next step, we finally have to print epoch as epoch plus 1 out of the total number of epochs, and then we have to print the train loss as train loss. We will get the first 4 decimal places, so train loss, this variable, and then shorten it to the first 4 decimal places, comma, train accuracy, the accuracy for training as train underscore accuracy, and then print the first 4 decimal places and put a percentage sign, comma, test accuracy, the accuracy for the testing data as this variable, test underscore accuracy, and then 0.4f decimal places. So now we can train our model. And if you want to get a pretty progress bar, you can go from tqdm.auto, import tqdm. We want to get the tqdm from auto library because auto will know that we are using Google Colab, and Google Colab is running a Jupyter Notebook on the cloud, so it will give us our an appropriate auto progress bar, not like the progress bar which is in the some editors. So it's a progress bar suitable for Colab. And then run the cell, we haven't specified that we want to put range and then epochs, and we have to call tqdm. So tqdm, and then pass range function and pass to range the number of epochs that we have. We have 10 epochs. Now we can run the cell. It is now training our model. So I think I will close, or I will turn off the video, and I will be back when the model finishes training. So now the training has finished, and as you can see, by reaching the epoch 10, the model loss, train loss 0.68, train accuracy 75%, which is nice. Now this accuracy indicates that out of 100 images, the model is able to correctly predict 75 images. And test accuracy, as you can see, 62. So that means the model is able to predict 62 images correctly out of 100 images. Now we have train accuracies, as you can see, train accuracies stored in a list. These are the accuracies across 10 epochs. Okay, for the train accuracies from 0.40, and the model goes on, or higher until 0.75. And if you check the test accuracies, the same idea, we have 10 accuracies across the epochs, but on the testing data. These are test accuracies. Okay, now we can plot these in a pretty line graph by going plot accuracy. So we will create plt.plot. Plot function will plot the accuracies across the how many epochs we have, and then pass train accuracies, which is a list that contains the accuracies over 10 epochs. And then the label equals train accuracy, the accuracy on the training data. The same thing, plt, so matplotlib library dot plot function, and we have to pass in here test accuracies to print them or to plot them. Label equals test accuracies, test accuracy. And then plt dot x label, we will define the x label as epoch. So epochs, across epochs, how the accuracy goes. And then plt dot y label, the y label will be our accuracy. So does the accuracy go any higher or does the accuracy go lower? We will now find out. And then plt.legend, we want to show a legend because we have set some labels, and we want to show these labels in a legend by using plt.legend function. Legend will show a legend. And then plt.title, the title, we will set the title as training and test accuracy. Training and test accuracy. And then last and finally plt.show, to show the plot or figure. Now let's run. Now we have this graphic that shows the accuracy. The train accuracy goes up and the test accuracy also goes up, but it's kind of plateaus here. So we can fine tune this model, but why don't we firstly show some predictions and then we can fine tune it to better the model, to make the model better performance. So now let's create a function to make predictions using our model. First of all, we have to create a function def called predict and plot grid. This function will take from me a model to use to make predictions, and will take from me dataset. Also it will take from me classes, what are the class names, and also grid size equals 3. Also we have to import random in order to choose random images and predict on. So import the library or import the package random. This function now, the first step, we have to set the model into evaluation mode by going model.eval, set the module in evaluation mode. So if you want to always to predict, you have to set the model into eval mode by using .eval function. And then we have to create a figure, comma, axes by using our subplot function. So subplot will create a subplot for each image. So each image will have a subplot. And then grid underscore size to define the number of rows, 3 rows, and we want 3 columns, as in here we have 3 rows, and also we have 3 columns in our figure. And then fixed size, the size of the figure will be a tuple containing 9,9. The first thing, we have to loop through our grid size. So for I in range of grid underscore size. Also we have to create an inner loop by going for j in range of grid underscore size. This loop will go through the columns. This loop will go through the rows, and this loop will go through the columns. And for each position in the rows and columns, we will have to create an index variable equals random.randint, starting from 0 to the length of dataset. So if you go length of our train underscore dataset, we have, or test, because we want to predict on the test underscore dataset, we have 10,000 images. We will pass this test dataset to this parameter, and then we will take the length of this parameter. So start from 0 until the length of dataset, comma, or -1. We have to -1 here because the last will be excluded. The next step is we have to extract an image and the true label, the true underscore label, by going dataset at index idx. So we want to extract the generated integer, to extract its index from the dataset, and then unpack the image and the label into these variables, image comma true underscore label. Input underscore tensor, the input tensor will equal image dot unsqueeze. We have to unsqueeze the image. Why? Because we want to use it with a model. Our model expect batches, expect data to be in the form of batches, so we have to unsqueeze it to get the dimension 0 to be the batch size. If you try here, we have test underscore dataset at index 0, for example. Test dataset at index 0, we will have this tensor. This tensor, if you want to know the shape of it, we can go dot shape and 3 channels by 32 by 32. So Pytorch likes the channels to be first. So channels first, 3 channels, 32 height, 32 width. And this channel and these channels, we want to add also a dimension or a dimension before it for the batch size by using unsqueeze. Dot unsqueeze dimension 0, and then if you get the shape, we will get a batch size of 1. So unsqueeze, important function. And then dot 2, we have to move the image to the device. Why? For the model to be able to compute on the image, to predict on the image has to live on the same device that the model lives on by going dot to device. And then with torch, we will use torch dot inference mode. So we will use our inference mode function. Why? Because turn off the back propagation algorithm to make the prediction faster and to make the code speed up more speed ups. Output equals our model, and then pass to it our input tensor. So input tensor will go through the model will make predictions and store it in the output variable. The next step is we want to emit this variable, and we want to use this variable predicted equals torch dot max function. The max function will take output dot data, and we have to specify here 1. Now we have to go outside of the with torch inference mode context manager and define the image equals image, but divide it by 2 and then plus 0.5. Why? We have to unnormalize the image, because currently if you look at one of our images by going test dataset at index 0, we will get a tensor for image, and you can notice we have negative values, and Matplotlib doesn't deal with images with negative pixels. So we have to unnormalize it by dividing it by 2 and then adding 0.5. Now you will notice these negative pixels will become positive. As you can see, it has become positive. So we have to unnormalize it. Unnormalize our images. Normalize our images to be able to plot them with Matplotlib, or to be able to use them with Matplotlib. And then NumPy image, we have to turn them into NumPy, because why? Also, Matplotlib doesn't work with Pytorch senses. Matplotlib deals with NumPy arrays. So you have to go NumPy image equals image.cpu. So we have to move our image to the CPU. Why? NumPy always do operations on the CPU. Dot NumPy method. And then axes at the axis of I, at this specific row and at this specific column, we want to show, we want to plot an image by going numpy.transpose. We have to transpose the image, because as you can see, our image shape starts with channels, and Matplotlib expects the channels to be last. So height, width, and then 3 color channels. So we have to align with matplotlib requirements by going numpy image and then passing a table of 1 to 0. We have to transpose the order of the shapes. Then we will define a variable called, for example, truth equals classes at index classes, which is this parameter classes that we have defined in here, classes, and we have to index on it, do some indexing, and then pass in here true underscore label. If it equals the classes for the predicted dot item, which is this prediction, so we will pass predicted dot item and index from the classes. If the prediction matches the truth, then this variable will become true, and if it's true, we will make the color equals green, else we will define the color as red to denote whether the prediction was correct or not. And then axes, we have to go outside of this else context. So it's important to be aware where you are writing code. You have to write it outside of the if else context here, and then we can go axes at index I, j dot set title. We want to set the title, or we have to set the title as f string truth, and then classes at index true label \n outside of the curly brackets, and then comma predicted, the model predicted classes at index predicted dot item, and then set the font size equals 10, the color as whatever the color variable was, whether it was green or whether it was red. The final step here, we have to set axes at index I, j dot axis off to prevent the axis from being showed, and then the last two steps, plt dot tight off. So plt dot tight underscore off, or tight layout, plt dot show. Now we can run our function and see what is the results of it. If you want to make predictions, we have to call this function by going predict, or by using predict and plot. Now we have created our predict function to make predictions using our model. The only step we have to do is we have to call this function by going predict and plot grid, and then pass our model, our trained model, and then pass our test dataset to make predictions on, comma, classes equals train underscore dataset dot classes, comma, grid underscore size equals 3. Now 3, 2, 1. Now we've got images, and you can see all of them are correct. So hooray, all of them are correct. Truth, truck, predicted, truck. And the truth here is cat. The model has predicted that it's a cat. Here truth is a dog, and the model has predicted that it's a dog, and so on, so on. So you can notice that our model has got all of these images correct. Truth, horse, predicted that it's a horse. Truth, cat, the model has make a prediction as a cat. So if you run again, you will get different images. Here, truth is frog, and the model has predicted that it's a frog. If you make some more predictions, we get color. I think color here, yeah, we have to set color as the variable color as color. Okay, run again. As you can see, we have some truth predictions, and also we have some wrong predictions. Why? Because currently our model accuracy, you can see here, the last epoch, the model test accuracy is 62%. So if you want to fine tune this model to get better results, we can do that by doing some data augmentation techniques. If you run more, you get some truth and you get some correct predictions and get some wrong predictions. Now we have this truth dog, and the model has make a prediction that it's a dog. Also here we have a correct prediction on the ship, truth ship, and the model has predicted that it's a ship. Now we can apply some data augmentation techniques to get better results. If you search here torch vision transforms, you will get a full documentation on transforming the images using Pytorch. So transforming and augmenting images. Torch vision supports common computer vision transformations in the torch vision.transforms and torch vision.transforms.version 2. Transforms can be used to transform or augment data for training or inference of difficult tasks. For example, image classification, detection, segmentation, and also video classification. So here we have a full documentation on how to augment images using a wide range of augmentations, including color augmentations like the class color jitter or random channel permutation. And also we have a wide range of functionals like horizontal flip or vertical flip. Also we have some padding, rotate, and a wide range of data augmentation techniques to apply on images. We can apply some of these techniques to fine-tune our model or to help the model learn better and to make the model more robust. So let's define some of these data augmentation techniques by going to the transforms variable. Here we have a compose class that contains just two data augmentations like toTensor and normalize. Why don't we apply some more data augmentation techniques by going, if you want to comment this, and then go transform underscore train equals transforms library dot compose. Compose let us train multiple image transformations in one hit. So we can pass a list and then define all of the data. So compose composes several transforms together. Okay, so the first transformation will be transforms dot random crop. We will crop the images. We will crop the images randomly by, you can notice here the size of crop will be 32, and you can read here about crop the given image at a random location. So you can crop the image at a random location. For example, you can crop the images of horses or of ships. For example, crop this segment of the image and just get this ship. So the model can learn the ship more better, or just learn the features about the ship. Learn the edges, the colors, the corners, the texture, and a whole bunch of different features that the model will learn about ships. Also the same idea with horse. The model, the data augmentation will maybe crop the image at the face and just get the face and let the model focus on the face of horses. So we will apply some random cropping on the images. So the class random crop takes from me the size of the crop 32, and then we have to pass also padding. Padding equals 4. Why padding? Here it takes from me two parameters. The first parameter size, the second is padding. If you want to read more here, we can read size could be a sequence like a list or integer. Here we have defined it as integer. Desired output size. So what is the desired output size? When you want to crop image, what is the size that we want to get? We want to get 32, and of the crop, if size is an integer instead of sequence, like height, weight, a square crop like size, size is made. And the second parameter, which is padding, here, padding, integer or sequence, optional, it's optional parameter, but padding or on each border, it will put padding on each border. So each border of the image default is none. If a single integer is provided, like this case, a single integer, this is used to pad all borders. So we will pad all of the borders by 4 pixels, comma, transforms. The second data augmentation technique we will use is random horizontal flip. So we want to flip the images in a horizontal manner, horizontally, okay, and then comma, we will transforms dot color jitter. Color jitter will randomly change the brightness of the image, also contrast, saturation, and a whole bunch of different, and hue of an image. So we can go define the brightness equals 0.2. We can define the contrast as 0.2. So these are all hyperparameters. You can play around, feel free to play around with these things. Also, these things are quite fun to play around with and try how the model will go on different settings of these things, comma, saturation as of the image equals 0.2, and then the last thing we have to pass in here, hue equals 0.2. Well, if the image is a torch sensor, it's expected to have 1 channel or 3 channels, comma, height, comma, width. Remember, always we have to start with channels. So these augmentations will apply on this kind of tensors. Start from channels, then height, then width. And then we have to apply our normal 2 tensor to convert the images into tensors. And then lastly, transforms dot normalize. We have to normalize images. Why? Normalization always helps with the model performance. We can set the mean as 0.5 and also set the standard deviation as 0.5, and we can run that safely. Now we need to retrain the model again. So we can get the dataset again, no problem. We can load our DataLoaders again. You can rerun all these cells and then build our batch embedding, also build our multi-layer perceptron class, our transformer encoder layer, and finally the vision transformer class, and then we will reinstantiate our model. Why? You have to reinstantiate because now the model weights. If you get the model .setDict, you will get a trained weights. So these are trained weights or trained parameters. We have to reinstantiate the model to retrain it on the fine-tuned or on the augmented images. So reinstantiate. Now the model is instantiated with random weights. If you check the weights now, they will be completely random. SetDict. These are now random weights again. Random weights. You can see the weight. The weights are all starting from 1. So random or crazy weights. Now we have to train it to make it better. The model architecture, the same architecture. We haven't changed anything in the architecture. We will keep the same cross entropy loss. We will keep the same parameters, the same learning rate. Also, we'll keep the same optimizer. We will not change anything. Just we will change the data and to augment it. Rather than from being just 50,000 images, we will augment them to make the model learn better. Reinstantiate the function of the train. Also redefine the function of evaluate. And then we have to retrain the model again. So retrain. It's now training on the augmented data. So I think now I will turn off the video, and when the model finishes training, I will be back. Now we're back. As you can notice, now the model has finished training, and the training accuracy now has gone higher by 1%, 76%, and test accuracy 64%. Before it was 62%. So we have improved our model. The accuracy has gone higher and the loss has gone lower. The loss was something higher than this. Now it's 0.65. Now we can make predictions using our improved model. If we check our train accuracies, we will get some different accuracies here. The first accuracy in the first epoch was 37%, but now it has improved until we have reached 76%. And for the test accuracies, the same thing. The accuracies, the first accuracy in the first epoch was 47%, and then we have improved our model going through the epochs until we have reached 64%. So as you can notice, the model has learned something. And the same thing if we replot our accuracies. Note how the patterns are going here. 3, 2, 1. Now the accuracy, the train accuracy is now going higher. Also, test accuracy is now going a bit higher than before. Okay, so we have improved our model. If we want to make some predictions using a model, we can use the same kind of setup of the code, and you can notice now we have these expectations. So truth, automobile, and the model has predicted that it's an automobile. The same thing here. You can notice that we have this image. Truth is a horse, and the model has predicted that it's a horse, and we have all these predictions truth or correct predictions. But for these images, yes, we do have some of them wrong, and that's reasonable because our model architecture or our model settings is now a bit small. For example, you feel free to play around with these settings. For example, try increasing the epochs to 30. So this is a homework for you. Try increasing epochs to 30, for example, and also try to make the image size, for example, transform the image, and make the size go to, for example, 2 to 4 rather than 32. Also, you can increase the number of heads. Try increase the number of heads to notice how the model changes from before. Okay, so feel free to change different settings and to play around with the code. If we rerun this, we will get different set of images like this. Truth is a truck, and the model has predicted that it's a truck. Also here, the same thing. So always visualize. You can learn more about your data by visualizing. So you can never know enough about your data, even though after building a model, you can learn that a model will behave some behavior on the data. So with that being said, we have finished and we have built our vision transform model from scratch using Pytorch. We have trained it first without data augmentation and the second experiment with data augmentation, and we have noticed slightly better performance. So I think we have finished this lecture. I hope you have learned new things, you have learned new codes, and see you in new lecture. So goodbye and thanks for watching.